Hola.
Como estes?
Life is. Oh, Dr. Dean, did you get that work that I get sent from my test?
I believe so, yeah.
Okay, yeah. I was like, because I know you said if you want anything extra, maybe, I think that's what you said, I don't know, but you said if you want proof of something to send you to work. I was like, God, please let this man give me just 2 points.
Yeah, it's for partial credit stuff.
Thank God, because I needed it, Lord. Then let me tell you how close I was to a dang 70. I made a 68.8. You talking about wanting to cry. I was like, listen, God, I just asked you to help me pass, please. And you gave me a 68.8.
Well,
Better than coronavirus. Better than coronavirus.
That's the raw score. So that doesn't include any partial credit. And also doesn't include any curving. So
I was about to cry. I was like, no, I'm getting tired of failing. I was like, I'm too close.
Hey, Dr. Dean, did you get my email?
About your internet?
Yes, sir.
Yeah.
Okay.
So yeah, just keep me updated on it.
What'd you say?
I said just keep me updated.
Okay.
Also, please remember to sign in by typing something in the chat. We'll give everybody another minute or so for any stragglers. All right. So we have been talking about light, some basic qualities of waves, and this should lead to a very obvious conclusion that waves and light are probably linked, or light is probably an electromagnetic wave, which is something that we have talked about before. However, light is really weird, and it's especially weird that so much about light is fundamental to how the universe works, and yet it is very odd seemingly. One of the main odd pieces of light is that light is a wave and a particle.
Dr. Dean,
Yes.
I have a question. Is that the last homework you're gonna post?
So the homeworks that are up right now are the last ones that are going to get posted. But
I saw you had added 3 more.
yeah, so with those, when you go through, if we have not talked about it in class,
because I did mine.
Mainly it has to do with the last chapter, 24. I'm trying to see how far we get to that, but yeah, so it will not be a full 24 will not be the full chapter, most likely. It'll just depend on how far into it we get. So yes, there are homeworks posted for this last
But chapters 22 and 24, right?
22, 3, and 4.
Okay.
Yeah. 24, it will be, like I said, it won't be the entire chapter, but it will be, I will be shrinking that down depending on how far we get through it. But that remains to be seen, like I said.
Oh my God, Mercedes hates me, man.
All right. So, all right. So, the nature of light. Light is both a wave and a particle. And this is fancifully called wave-particle duality. But it's kind of a misnomer. It's not that it is a wave completely and a particle completely. It's that it has a lot of overlap in the way it acts. So the way we treat waves and the way we treat particles are generally very distinct, very different. But the way we treat light, it has a little bit in common for both. So one issue that can kind of come up in this is when we're talking about energy. So you can kind of think about this as kinetic energy. Who remembers what the equation for the energy of an object is? Kinetic energy.
Kinetic energy formula?
Yes.
Okay. Let's see.
Did it have a 1/2 in it?
Did it have a 1/2? Yes, it did.
Yeah, 1/2 mv squared. That's the formula for kinetic energy, right?
Yes. That is the
The
formula
1/2
for
mv squared.
kinetic energy.
Because
Okay. So
yeah,
what does V stand for?
velocity.
All right. And what is the velocity of light?
Meters per second.
That's the units.
Yeah, because I checked the formula Because I know V stands for velocity is speed of object.
So what is the velocity of light?
Lambda F.
Okay. The velocity of any wave is lambda f. But what about the velocity of light?
Let's see. Velocity of light of vacuum. Ah, hold up.
Oh,
I think the velocity of light is the speed of light is in a vacuum. Something like that.
I know it's Monday, but
So
this lesson is already going right over your head.
because I already know the formula of kinetic energy.
You're thinking about it way too hard.
Yeah, guess so.
What's the question, Dr. Dean?
What is the speed of light?
Three times 10 to the 8.
3 times 10 to the 8th meters per second.
Oh,
Yeah, it is. I ain't want to answer it though. You know me.
Yeah, okay.
oh my goodness, man.
Dakota always got to be the smart one.
Nah,
He is.
I was just waiting to see.
He is.
Wait a minute, Dr. D. Hold on. You know I'll be asking questions now.
So when I said right over somebody's head, I meant mine. So I kept doing this, underlining it for you. Okay. So my black marker is dying out. So we know speed of light squared. What about the mass? What is the mass of light?
Hold on, wait a minute.
What is the mass of a wave? What is the mass of fire? So we'll go with
Say it
It's
again.
a trick question in a way.
kind of a trick question, but
It doesn't have no mass.
it doesn't have a mass. A wave, like even out in the ocean, the wave doesn't have a mass, right? Like it has water, but the water isn't the wave. The wave is the interaction. It's the motion of that water. But the water was there before, and the water's still there after the wave goes through. So the wave doesn't have any mass to itself. It's just an interaction. So what is the energy classically of a wave? Or in this case, a wave of light.
0.
0.
0.
Yeah.
0.
1/2 times 0 times c squared is
Anything times 0 is 0. Come on.
So-
now.
exactly. So this creates kind of a weird problem for us because light does have energy and waves do have energy, but it's not done classically like we're used to, where we have 1/2 mass velocity squared. So this doesn't work for us. It doesn't work for light, because light is not just a particle. It can also be considered a wave. So we have to look into its wave characteristics to figure out the energy. And we will say that they did, and I'm not going to go through all the math of it. I'm just going to give you the answer. The wave is entirely dependent on the frequency. So energy equals H times F. This
Lord.
H is a very special H. Ooh. So H is called Planck's constant.
What? I feel like I've heard that before.
I'm sorry?
I feel like I've heard that before.
So it's something that definitely appears in a lot of sci-fi stuff, because it is a big deal and it governs a lot of higher end physics, from E&M to quantum mechanics to, all sorts of different things. And especially quantum mechanics, Planck's constant pops up a lot. But it is 6.6 times 10 to the negative 34 joule seconds. So, trying to decide how much I want to really get into the Planck's constant stuff. Really, at this point, just kind of accepts that it's there, because there's a lot of potentially very emotionally upsetting math behind it. But just recognize that this is where the energy of light comes from. So the energy of a photon is Planck's constant, H, times the frequency. So let's take this idea and look at it a little bit more. So E equals HF, all right? So if I have a high frequency, what does that mean about the energy of that photon?
That is high. There's a lot of energy going on.
There's a lot of energy. Also means, vice versa, that if we have a low frequency, it has low energy.
Correct.
In order to create that photon, if it has high energy, then you need more energy. If it has low energy, then it doesn't require as much energy to make it. Now let's see, how are frequency and wavelength related?
Connect. Because if the frequency, let's say the frequency is like, I guess, from the peak to the drop, like, and how often it does that, correct?
So the frequency is how often it repeats.
Yeah.
A cycle,
Yeah.
yes.
You said how does that go hand in hand with the wavelength?
How does frequency and the wavelength of the light relate to each other?
Because if because the frequency is pretty frequent, then the wavelength's going to be. Ooh, that's tough. Actually, I don't know.
Okay.
I
So
feel
we
like
have
I was
a
on the
high
track in there.
frequency. What does that mean about our wavelength? First off, is there a relationship that has F and lambda in it?
Yeah.
We talked about that Friday, innit?
Hmm.
When I said something about like like it's more like frequent in the wavelengths, like like more of it go up.
So yeah, you brought up that if it's doing it more frequently, then something happens to the wavelength. But there's an equation, a relationship between that has F and lambda in it. What is that relationship? Can anybody think of
You talking about C equals lambda
C
F?
equals lambda F. Very good. So, in that equation, because C is constant, it is a number that does not change. What happens if you make F big?
The lambda be big too, or it'd be small.
It would be small.
I was like, there's only two ways you can go with that. So
Yeah.
if it's not the first one, it's
So you're 50-50. But yeah, so this is what we talked about on Friday. Because the speed of light is constant, if you make lambda big, that means you make F small. Or vice versa. If you make F big, you make lambda small. So high energy means small wavelength, and small e is high, or we'll say big, large wavelength. Okay? So we talked the other day about the spectrum of light, and we said that for really long wavelengths, that's like radio waves where they're like, half a mile long sometimes. And then if you go all the way to the other side, you get into ultraviolet, which is on the order of a few nanometers long. So ultraviolet rays have a lot more energy because they have small wavelength. Ultraviolet, the ones that are harmful from the sun, have a very small wavelength, which means that each individual photon has a lot of energy. Radio waves that have large wavelength have a very small energy. So this is, it's definitely not the end all be all, but this is one of the reasons why things like ultraviolet radiation and above that into gamma radiation, which has even higher energy and smaller wavelength. This is part of why they say use sunscreen, because if you don't use sunscreen, you'll get sunburn, but you'll maybe develop skin cancer, something like that. So high energy light can be very, very harmful to you because you're constantly getting pounded with all of this energy. But except for a couple, tin foil hat type people, nobody's ever said that radio waves from like FM radios have any effect on your body. And it's partially because, we'll get into the other reason why a little bit later in this semester, or in this section, but it's part of because those long wavelengths have a very small amount of energy associated with them. So this is something that you see on a day-to-day basis, is just because of how the energy of light and everything works, you have high energies, small wavelengths, small energies, large wavelengths. So this is the idea, that the energy of a photon is Planck's constant, which is this h times the frequency. So high frequency, high energy. Low frequency, low energy. All right. So let's continue on with this wave-particle duality and talk about so reflection and refraction. We'll start off with reflection. What is reflection? What does that mean? What does it mean to reflect?
It means to think about what you've done throughout your life and think of how you could have changed it. No,
Okay.
on the serious note.
So it involves you looking back.
It's like throwing back a bomb.
So that's a mental thing, and it is actually related to what's going on physically. But
it's like a mirror image that sends back to you.
Okay, so a mirror shows you your reflection.
Yeah.
So let's look at that. So, and my markers are dying. Isn't great, but that's where we are. All right. So say this is our mirror, okay? Light comes in, hits the mirror. When a light ray comes in and reflects, it just bounces straight back. All right, so this one going this way, this one going this way. So this is how something would reflect if it went straight into the mirror and then straight back. So this is something that objects kind of go through too. So this is that particle, wave particle kind of duality of light, where if it comes straight in, it bounces off. But what if it came in at an angle? What would happen?
The same thing what happened, it still bounce off of an angle.
So it bounce back.
Nah, I think it'll bounce down.
So yeah,
Like a V.
it'll make like a V. So it acts kind of just like if an object went in. If you had a ball that rolled in and hit something, like a pool ball, let's say, hits the edge of the table, it's going to bounce back something like this, right? So this is exactly how reflection works. Something comes in, bounces off that medium, and comes back out. Now, refraction is the other side of things. This is how a lot of things, different things work this way. But like two-sided mirrors, or one-sided mirrors, I don't know, I guess what the technical term is, where on one side you see a mirror. On the other side, you can actually see through it, right? And when light hits something, some of it reflects, but then some of it actually refracts and goes through it. How do I want to do this? We'll do it like this. Okay. So refraction, that's why it's on this side. I guess I should have drawn the mirror more in the middle. Reflection happens when a light ray comes in and then bounces off. Refraction happens when it comes in and then keeps going. But what's something that's kind of interesting about the green arrow compared to the black one?
It's not as lined up. Like, it's not a straight line. It's like a broken.
It's not a straight line all the way through. This is a quality of refraction. And again, we're going to get into the technical parts of this next time. This is a quality of refraction. Refraction generally bends the light as it goes through something. So you have an incoming light ray. Part of it hits the glass and bounces off at an angle like this. Part of it will actually go through and bend. So this refraction thing, does anybody know of a very famous example of this, or an object that does this very well?
Sunglasses?
So they actually diffract more than refract.
What about like a glass of water or something like that?
So
Or normal
glass
glass.
of water can do it to a certain extent. The image that comes to my mind is, so I'm opening it up to share. This one. Who all has seen this thing before?
Pink Floyd?
Me.
Oh me. I remember this.
Okay, first off,
It's a
yes,
prism. It's a prism.
absolutely, Pink Floyd. Well played.
It's a prism.
But this is a prism, and
Prism.
this is refraction in all of its glory. So there's a lot going on here that we'll discuss. But you can see that a single light ray comes in, and then it hits, and it bends. But when it bends, something strange happens. This white light has red, orange, yellow, green, blue, violet. All of these light rays were all together right here. So when it comes in and it hits, how it gets bent is different depending on the wavelength or frequency, whichever way you want to describe it, of the light that gets bent. So the red one is closest to the normal one. So if we had kept drawing this, it would look something like that. The red one is closest to that. And then orange, yellow, green, blue, and the violet one is the most different from that.
Is that called like the electron spectrometer or something like that?
So electrospectroscopy is slightly different, but it
Okay.
does actually, I mean, you could kind of say it's a little bit related to this, but it is, it's a little bit higher order. But this is a spectrum. So that's a good jumping off point. A spectrum is a set of all of the possible values of a, in the case of light, of all of the wavelengths between two endpoints. So, but who remembers red versus purple? Which one has the highest or the largest wavelength?
Red.
Red.
Red. Roy G. Biv. Red.
Yeah,
Red the
red.
highest and violet's the lowest.
Yeah, and because it's inversely related to energy, purple has the, or violet, has the most energy, and red has the least energy. So this bending, this refraction, is very much based on how much energy it has. This is responsible for all kinds of different effects. One common one is that it's why we see blue in the sky. The sky is blue because of this principle. And we'll get more into hows and everything. But just understand that refraction happens. So light gets bent as it goes through some medium, whether it's plastic or someone mentioned water does this. It does. It causes light to bend. And the amount that gets bent is more, the more energy that light has, the more it gets bent. The less energy, or the longer the wavelength it has, the less it gets bent. So this is the idea behind reflection versus refraction. So reflection bounces off, refraction, it goes through and bends. So like I said, we will get through and go into each of these more in detail this week. And if you guys have any questions, then come and see me at my office. Send me a message, or I can jump on and we can chat about something. But yeah, so this is our stuff on